To train a world-class machine learning model or power an executive dashboard, you have to feed it clean data. But the raw data an AI engineer inherits rarely starts out that way. It is tempting to think of an enterprise database as just a giant Excel spreadsheet, where every detail of every transaction is logged on a single, massive grid. Logging millions of daily transactions onto one flat table causes severe duplication. If a single customer makes 50 purchases a year, their name and address are stored 50 separate times. The database becomes bloated, sluggish, and vulnerable to structural errors if you ever need to update a single record. Database engineers solve this by choosing to shatter that grid. They break the data apart into isolated pieces called dimension tables. One table strictly holds unique customer details, while another exclusively holds product information. This design is highly efficient. But it introduces structural tension. Your information is now perfectly safe, but completely fragmented across empty space. To navigate these fragments, data scientists rely on SQL. It acts as a precise grammatical toolkit that lets us extract specific pieces of information from across the system without ever having to modify the underlying database. A data scientist's expertise lies in this logical reconstruction, the ability to stitch these shattered fragments back into a single, cohesive view. Using the select command, we target only the specific vertical columns we need for our model. Then we apply a where clause. This acts as a strict filter. Any row that doesn't meet our exact conditions is instantly stripped away. When we are dealing with messy text, we pair this filter with the like operator. By adding wildcards, we can hunt for partial text matches hiding inside massive datasets. Say you are searching a massive movies database to isolate a specific character. You instruct the engine to find any record containing the word Thor anywhere in the title, and it ignores whatever text comes before or after it. By applying these strict filters up front, we guarantee our algorithms process strictly relevant data, preserving vital computational memory. Filtering gives us specific rows, but business intelligence often requires understanding the big picture rather than scanning millions of individual entries. We use the group by clause to zoom out. This command takes scattered records and magnetically bundles them into manageable categories based on shared attributes. Then, mathematical functions like min, max, and AVG instantly calculate key metrics for every bundle. By pushing these mathematical calculations directly to the database level, your local machine never has to pull or process those massive datasets manually. Things get more complex when a report requires data from two completely different places, like generating a list of Bollywood movie titles alongside their total revenue. The titles live in a movies table, and the revenue figures live in a financials table. Pulling from either table independently will fail to provide a complete picture. We solve this with the join clause. It builds a bridge between isolated tables using a shared link, snapping records together. For many-to-many relationships, database architects insert a mapping table. This cleanly routes connections between unique IDs, avoiding text duplication. The join clause allows us to cleanly map these fragmented dimensions back together, packaging the data perfectly for machine learning ingestion. Even perfectly joined tables often hide internal inconsistencies. A financial record might list revenue in billions for one row and thousands for the next. We catch this using a case statement. This logic tree evaluates every row, dynamically scaling mismatched units up or down to a single standard. We wrap those normalized figures into a newly calculated column, perfectly standardized before leaving the database. The final step is simply exporting this heavily filtered, standardized, and perfectly bridged record set as a flat CSV file, ready for Python. SQL serves as the essential translation layer, turning fragmented storage into the structured, reliable feed required for accurate machine learning.